corresponding orbit moving in the other directions also. So why all these things are required for diamagnetic material is so that the total spin moment is also zero, and the total orbital motion is orbital momentum, angular momentum is also zero. So when both of them are zero, the total value of the magnetic dipole moment is equals to zero when no field is applied. But when you applied a magnetic field, then we have seen in the last class, then it acquires a negative magnetization. So those were diamagnetic materials. But today we are going to talk about the paramagnetic materials first, and then later we'll talk about the ferromagnetic materials. So uh, if you can see this first picture, we have what are called as paramagnetic materials. In the second picture here at the bottom, you have ferromagnetic materials, then you have antiferromagnetic, and finally you have ferrimagnetic material. So in all these materials, you can see that you have permanent dipole moments. That means whatever constituents you have, they have a permanent dipole moment, which means that that dipole moment is not dependent upon the magnetic field. The net magnetization will depend upon the whether the magnetic field is applied or not, but they individually have some dipole moment, which are shown by arrows over here. Okay, so paramagnetic material is inherently different from ferromagnetic, antiferromagnetic, and ferrimagnetic. How they are different is that these dipoles, we will assume there is a theory called as Langevin theory that we will read about later on, and we will assume that these dipole moments are localized. Localized means that if they are on an atom, they stay on that particular atom. They are not moving around here and there in the solid. Okay, and the other thing is that there is no interaction between them. No interaction means what? No interaction means that orientation of one dipole does not depend upon the orientation of the other dipole. That means they are completely free of each other. One dipole does not affect the other dipole. So in that case, we call that material as paramagnetic material. What are ferromagnetic materials, or what is the difference of paramagnetic material with respect to these other two kinds of material is that in these other type of magnetic materials, there is an interaction between them. That means that if one of them is, let us say, in the spin up direction, then the other will be affected by the direction of that particular magnetic dipole moment. So if the interaction is such that they favor parallel alignment, then those kinds of material are ferromagnetic. If their interaction is such that if one of them is pointing in up, then the next one will be pointing in the downward direction, such that the net magnetization is zero. In that case, we'll call those materials as antiferromagnetic. In case of ferrimagnetic materials, again, if one of them is, let us say, spin up, the other one will be spin down. But in this case, you will find that they are not equal and opposite to each other. They are opposite to each other, but they are not equal in magnitude. And therefore, the net magnetization is not zero in case of ferrimagnetic material. So if you remember in the last class, I told you that ferromagnetic material and ferrimagnetic materials are very similar to each other. Why? Because both of them have some magnetization which is not equal to zero, or net dipole moment which is not equal to zero. But the net dipole moment in this case will be zero, and in this case also you will find that if I find the average value of the dipole moment, that will turn out to be zero. Why they will turn out to be zero? Because if there is no magnetic field applied to it, then all of them are pointing in random directions. So if you take an average of them, then their dipole moment will turn out to be zero. So that is the difference between paramagnetic, antiferromagnetic, ferromagnetic, and ferrimagnetic materials. And what we will, as I said, what we will discuss here is paramagnetic materials. Now, in paramagnetic material, remember what I told you was that the dipole moment of one of the dipoles is independent of the dipole moment of the other. Certain situations may arise where the exchange interaction, the interaction that I was talking about, that is called as the exchange interaction, which I will represent by letter J, that exchange interaction may not be zero. That means that you have a material where the spin of the one of the atom is affected by the spin of the other one. So there may be some interaction, but sometimes what can happen is that the temperature is so high, that this interaction is very, very small as compared to the thermal energy, which is represented by KT. So when this thing will happen, and this thing happens in ferromagnetic also, for ferrimagnet also, and for antiferromagnetic also. That means you have increased the temperature so much such that this condition is satisfied. And you will find that when this condition is satisfied, then all these materials will also start behaving like paramagnetic materials. So as I said before also, what happens in case of paramagnetic material is that when you have not applied any magnetic field, then all of them are pointing in the random directions. And if you look at the average value, that average value will turn out to be zero. But when you have applied the magnetic field, they are still pointing here and there. But overall, they will acquire some dipole moment along the direction of the magnetic field. That means you will acquire some value, okay, which will not be equal to zero. And this net dipole moment will be proportional to whatever external field you have applied. Okay, and the dipole moment, this magnetic dipole moment, will be in the same direction as your applied magnetic field. Okay, so that means if I look at the susceptibility, then for the paramagnetic material, the susceptibility is some positive number. Okay, and if you remember from the last class, that this positive number is of the order of 10 to the power minus 3 to 10 to the power minus 5, the magnetic susceptibility for paramagnetic materials. Now we will talk about what is called as the Langevin theory of paramagnetism. So in Langevin theory of paramagnetism, what we assume is that assumption is that you have, okay, number one, you have localized dipoles. So you have localized dipoles, and the second assumption is that the dipoles are independent of each other. Okay, so these are the assumptions for the Langevin theory, that you have localized dipoles and those dipoles are independent of each other. So when you are applying magnetic field, if you remember in this particular slide, I showed you that even if you apply the magnetic field, in that case also, the alignment is there. Yes, some slight alignment is there, but there is not a complete alignment. That means not all of them are pointing in this direction. That is not the case. Okay, even though whenever you place a dipole in some magnetic field, then some torque acts on that particular field, on that particular dipole. Okay, and what that torque tries to do is it tries to rotate all the dipoles along its direction. But still you can see that all these dipoles are, yes, some alignment is there, but complete alignment is missing. Why complete alignment is missing? Because this torque, which is also represented by this energy, which is written as minus of m dot b, where m is the dipole moment and b is the magnetic field. So this, either you can say because of this energy, or you can say that because of this torque, the magnetic field tries to align these dipoles along its direction. But there is a thermal energy also. So there is another energy which is represented as kBt. Okay, so this is called as the thermal energy, and this has a randomizing effect. So you will find that there are two competing forces here. One is that it tries to create order, okay, and this energy tries to create disorder. Okay, so dipoles are basically torn between these two interactions, these two competing interactions. One is which tries to align everything in one direction, and the other thing tries to randomize everything. So these are the two competing mechanisms which are there in Langevin theory also, that you have minus of m dot b, which is the energy, magnetic energy of the dipole in presence of this magnetic field, and the other one is the thermal energy. So how do we know? How do we calculate this average value of magnetization? So that is what Langevin theory is about. So let us see how we can do this. So what we are going to do is what is called as the Maxwell-Boltzmann distribution. So what this Maxwell-Boltzmann distribution says is that if you have a system, okay, and there are several energy, let us say energy levels are there, okay, and if I ask you this question, that what is the probability that this particular level will be occupied by the system whose energy is U? What is the probability of occupation of that energy level at temperature T? So that question is answered by this expression, which is called as the Maxwell-Boltzmann distribution. It says that the probability of occupying of this particular state will be given by exponential of minus ratio between U and kBT. So again, you can see that there is this competition between this internal energy part and this randomizing energy part. Okay, so that is given by the Maxwell-Boltzmann distribution. So let us say that you have several dipoles inside your system, just as it was shown over here, that you have several of these dipoles over here. Okay, and they will be pointing in all sorts of directions. Now I want to check what is the probability of them pointing in a certain direction, which is making some angle theta with the magnetic field. So here the magnetic field is shown to be in the vertical direction, but in this you will see that the magnetic field is shown to be in the horizontal direction. So I will assume that my magnetic field is pointing along this x direction. You can say, you can call it x direction if you like, but this is the direction of the magnetic field. Now, what is the probability that my dipole will be pointing along this direction, in some direction which is making an angle of theta with respect to the magnetic field? I want to calculate the probability. So what I will do is I will draw a sphere, okay, and I will take a slice. So I will take a circular slice of this particular sphere. That slice is shown over here. Okay. So if this distance is, let us say, r, the radius is r, then this particular radius, this radius will turn out to be r sine theta. Okay. So you have a circular strip of radius r sine theta and whose thickness is r d theta. Okay. Now this strip will extend some solid angle onto this point O. Let us call this point as O, and I will call that solid angle as d omega. Okay, and this d omega angle is given by 2 pi sine theta d theta. Okay, so the probability will be now proportional to this Boltzmann factor and this solid angle d omega. So if I include both of them, then you will find that the probability of alignment will be given by exponential. All right. Now what I will do is, instead of u, I will write this value. All right. So it will become mb cos theta, because m dot b is mb cos theta over kbt. All right. And then d omega, which is 2 pi sine theta d theta. So this will give me the probability of alignment of a dipole along this particular solid angle. That means pointing in a solid angle defined by this particular circular strip, which is shown here. So this is what this probability will be equal to. Now, if the dipole moment is, let us say, m, okay, it is pointing in this direction and its value is m, vector m. Okay, but what I want to do is I want to calculate the component of this dipole moment along the magnetic field. So I hope you will agree that if this is m and this angle is theta, then this component will become m cos theta. Okay, so what I want to do is I want to calculate the average value of the dipole moment. That is what I want to calculate. So how I will calculate that average value? I will calculate that average value as I will integrate. I will integrate later on, but let me first write the expressions first. So what I will do is I will take m cos theta and I will multiply this thing with this whole probability. That means exponential of Okay. And I will divide with something else that I will show you later on. But now what I will do is I will integrate from theta equals to 0 to theta equals to 5. So this will give me component, the component which is along the magnetic field B. But what I have to do is I have to divide by the overall probability. What is the overall probability of aligning anywhere in this whole sphere? And that probability will be given by integral from 0 to pi exponential of mb cos theta over kt into 2 pi sin theta d theta. Okay, so this is the mathematical expression that I have to solve here. And you will see that this 2 pi and this 2 pi will get cancelled. Okay, and if you know a little bit of mathematics, then you can find out this integral by integrating them by parts. So my aim is not to go into the mathematical details of all this, but the integral is actually fairly easy to solve. So what you can do is that in this particular integral, you can put mb over kbt, you can put it equal to, let us say, x, and you can put some cos theta equal to y. And if you do that, then you will find then this value of m bar will become m integral from -1 to +1 e to the power xy y dy upon integral from -1 to +1 e to the power xy dy. Okay, and from these two terms you will find that in the numerator you had this extra term of pi over here, which is not there in the denominator. Okay, so as I said, that you can solve it for yourself, and hopefully what you'll find is that this whole thing is equal to this whole thing will be equal to e to the power x plus e to the power minus x over e to the power x minus e to the power minus x minus 1 over x. Okay, and this is the cot hyperbolic x function. Okay, and therefore the final result that you get is this one. Okay, so the final result is written over here. Okay, and you can see that this lx function, acha, I forgot to multiply with m over here, so I have to multiply this whole thing by m. Okay, remember what was m? M was the actual dipole moment of the dipoles. So here you will see that this average value of magnetization is equal to magnetization multiplied by this factor. Sorry, not magnetization, dipole moment. So the dipole moment, the average value of dipole moment is given by the actual dipole moment multiplied by this function, and this function which is written as Lx over here. This function is called as the Langevin function, which is the Langevin theory that we are talking about. Okay, so this function is the Langevin function, and this is equal to this expression cot hyperbolic x minus 1 over x. Okay, so let us look at this Langevin function, and remember the average value of m is given by m multiplied by the Langevin function. And what is the value of x? X is mb over kt. Okay, so x is in a sense, uh, uh, how should I put it? Uh, it is in a sense trying to parameterize that which one is dominating, whether the order creating magnetic field is dominating or the randomizing thermal heat is dominating. If x is large, that means you can expect higher order. Higher order means that more and more dipoles will start to align along the magnetic field if the value of x is large. But if the value of x is small, then you will find that the dipoles will be pointing in all sorts of random directions. So that is what x tells you. That what is the order, how much order you can expect inside the system. Okay, so that is the value, that is what x represents. And remember that this is the main result according to the Langevin theory, that it is equal to the actual dipole moment multiplied by the Langevin function. So let us look at this Langevin function. What does it look like? So this is what this Langevin function looks like. This is this is how the Langevin function looks like. Okay, so you can see that I've plotted Langevin function as a function of x. That means as the order is increasing. How can you increase the order? You can increase the order either by increasing the magnetic field or by decreasing the temperature. Okay, so that is how you can increase the value of x, and you can see that as the value of x is increasing, this value is increasing, all right, and its saturation value, its maximum value will be 1. Okay, so what will 1 represent? If you remember that the average value of the dipole moment was given by m multiplied by x. So if Lx is 1, if Lx equals to 1, then this would imply that the average dipole moment is equal to the actual dipole moment. That means that all the dipoles are now aligned along the magnetic field. Okay, but you can see that it is very difficult to make it 1. Okay, because this thermal, this randomizing energy is always there. Therefore, you will always find that it becomes difficult to get this value of 1 over here. So that is the Langevin function, and that is the Langevin theorem. What you can do here is that at small values of x, that means when your mb, this mb, when this is very, very less than the thermal energy, in that case you will find that this Langevin function is approximately equal to x by 3. That means the slope is equal to 1 by 3. Okay, in that case, if you have this x very, very less than 1, then this would imply that Lx will be approximately x over 3, and this would imply that m bar, okay, so that m bar will be equal to m into x by 3. That will be equal to m into, if you remember what was x, that was equal to mb upon kt. So it will become 3 kt. That will be the average value of the dipole moment. And from the average value of dipole moment, you can find out the magnetization. What will be the magnetization? Magnetization will be the concentration of the dipoles multiplied by the average value of the dipole. So this becomes nm square b over 3 kbt, right? So this is the value of magnetization. And how do you find out the value of uh, magnetic susceptibility? The magnetic susceptibility is found as, if you remember, was equal to magnetization over the auxiliary field. And what is the connection between auxiliary field and B? So that is equal to, let me write it like this, B over mu naught. So now what you can do is you have already found the value of magnetization. Okay, so this was the value of magnetization. You can substitute this value of magnetization into this equation, and finally what you will get is this susceptibility. So this will give you the classical result or the Langevin value of the susceptibility. Okay, and in this case you can see that what it is telling you is that everything else is some constant, right? The only variable that you have in your hand is temperature. So this is called as the Curie law, and this Curie law says that chi m varies as 1 over T. That means if you look at the susceptibility chi m, then it will go down like this. Okay, so this is called as the Curie's law. So whenever we are writing Curie's law, so generally we write it like this. We write it like this, as some constant upon temperature. And what is the value of constant? This value is equal to everything which is over here except for temperature. That's what this constant C is. So this particular thing is called as Curie's law. Now everything, all these things were classical results. What happens quantum mechanically? So quantum mechanically, not much difference happens. The only difference that happens quantum mechanically is that instead of m, you write this particular m as the Landé G factor j plus 1 h bar. Okay, h bar will be consumed in that Bohr magneton. So we write it like this. Okay, so that is what this quantum mechanical expression for the dipole moment becomes. So if you make that substitution, then you will get this particular value, which is the quantum mechanical approximation for this Langevin theory. All right, and you can see that the only change we have made is that instead of m, we have written this particular quantity. Okay, so this is the quantum mechanical expression for the Langevin theory. So whether it works or not, you can make that calculation. So that calculation is shown in this particular table. So in this table, you will find that for different ions, the value is calculated. Okay, this is the value of G into J plus 1. The configuration is also written over here. All right, and this value of J over J plus 1, you can assume this to be the theoretical value. Okay, according to the Langevin theory, or quantum Langevin theory, you can say if you like. So this is the theoretical value, and this is, you can say, is the experimental value. Okay, and you can see that are they agree quite nicely. One of the differences, this particular thing, it says that for europium, the theoretical value should have been 0, but it actually turns out to be 3.14. The reason is different because this value is calculated assuming the ground state. Okay, but in actuality, the European ground states has some other states which are very close to energy. So those states are also populated, and therefore this value is actually different from 0. So if we neglect this European part, for which I have provided an explanation, the correspondence is quite well. And remember, these are rare earth ions. Okay, so that is what it is written over here. We are talking about rare earth ions here. But by the way, what is so special about rare earth ions is if you focus on this particular orbital, any of these orbitals. So you will find that f orbitals are partly filled. Okay, so they have partly filled f orbitals. Okay, so what is special about f orbitals? Why we are talking about f orbitals and not s and p orbitals? F orbitals are extremely localized. Localized means that when they form a bond, then they do not participate in bonds. The bond formation takes place only via the s and p orbitals. Because f orbitals do not participate in bonding, therefore the electron configuration does not change in the solid state form. And therefore, their electrons, they behave like spins. For example, for cerium, you will have, it can have, for example, 7. All right, so it will have one of the electrons, and for example, praseodymium, so 4 of them are there. Okay, so in this case, you expect a magnetic moment of 1 Bohr magneton, and in this case, you expect a magnetic moment of 4 Bohr magneton if we focus only upon the spin of the particle. But this is not true. You have to take the total angular momentum here. That means that you have to consider spin also and the orbital also. Then only you can arrive at the right value of the right experimental values. Okay, so why we are focusing on f orbital is because with bonding they are not disturbed. So their spin is intact, and therefore it is easier to deal with such kind of materials. But similarly, d orbitals are also localized, but those orbitals are not as localized as f orbitals. So what happens in case of transition metal ions, where you have partly filled d orbitals? So let us look at that. So if you look at the transition metal ions which have partly filled d orbitals, okay, in those cases what happens? So now if I calculate this value of J plus 1 multiplied by this Landé factor, G factor, and if I compare it with the experimental value, you will find that these values generally do not agree with each other. Okay, so these values will not be agreeing with each other. But what does happen is, if Instead of taking the value of J, which contains spin and orbital both, spin plus orbital, it contains both. If you take only spin, means you just neglect the orbital part. Okay. Now, if you compare the values, you will find that the values are in a better agreement with each other. Okay. So it appears that for transition metal ions, the magnetization is arising only because of the spin of the particles or the spin of the ions, and the orbital part seems to be gone. It is missing. It appears that it is completely missing. Okay. So why that is happening? Okay. By the way, this phenomenon where the orbital part is almost zero, this is called as quenching of the orbital angular momentum. It is as if you have quenched the orbital angular momentum. So why this happens is because of the crystal field effect. So whenever a transition metal ion, let us say you have a transition metal ion, all right, and it is surrounded by, let us say, 6 oxygens. Okay. In that case, these oxygen ions, which have some negative charge in this particular case, okay, they create some electric field on the transition metal ion. And that electric field is called as the crystal field. So what happens because of this electric field is that whatever orbital motion is there, that orbital motion cannot reorient itself on the application of magnetic field. That means it gets stuck because of this bond formation with the oxygen. All right. And because it cannot be rotated, therefore it does not contribute to the dipole moment of the solid or the ion in this case. So that is why what you will find is that in case of transition metal ions, the orbital part, this orbital part is equal to 0, which is what I was calling as quenching. It is as if we have quenched the orbital part, and therefore it is sufficient to focus only upon the spin of the ion. And because the coupling between the spin and this crystal field is very weak, therefore that spin is not too much affected by the electric field. So if, for example, someone asks you that for Fe2 plus, what will be the, if Fe2 plus ion is present inside your material, then what magnetic moment you can expect? All right. So I will draw the d orbital of it. Okay. It has 6 electrons. The configuration is d6, and you will find that this will be like this. Okay. So I have neglected the crystal field effect here. I don't want to go into those complications. I'm assuming that that is 0 for the time being. And if I look at only the spin only moment of this particular ion, then the spin only moment of the ion, you will find that it will be equal to 4 Newton. That means you can expect that your ion will have a magnetization, or sorry, a magnetic dipole moment of 4 Bohr magneton. So this is what happens in case of transition metal ions, and this is the reason why quenching takes place. So remember, if you are dealing with the rare earth ions, you have to include both. You have to include spin plus orbital. That means you have to work with this quantum number J. But in case of transition metal ions, it is sufficient to take spin only. It is sufficient to take only spin. All right. And therefore, you can focus only upon the spin of the transition metal ion. So that is called as the quenching. All right. So just 1 minute. So this is what I'm talking about is all these things are maybe true for several sorts of rare earth ions and several sorts of transition metal ions. And this is we are right now talking only about the Langevin theory. Okay, where you have localized dipole moments and they are not interacting with each other, and then there is a thermal randomization process. So we have seen that in that case, chi-m varies as the Curie's law. It varies as 1 over T. It decreases as 1 over T. Now there is another kind of paramagnetism in the system, which is actually temperature independent. That means if you increase the temperature, in this case you saw that the magnetization or the value of chi, that varies as 1 over T. Okay, that was the Pauli principle. Okay, so if you look at that susceptibility, then I told you that it will look something like this. Okay, and if you remember in the previous class, I told you that the intercept, if the intercept of 1 over chi m versus temperature, if it is passing through the origin, then we call that as paramagnetic material, which is basically same as Curie's law. So that is what we generally expect. That, but in case of Pauli paramagnetism, if you look at the temperature of the magnetic susceptibility versus temperature, it is almost constant. That means it is not changing with temperature. So why that happens and when that happens, that is what we will discuss next. So let us talk about Pauli paramagnetism. So this Pauli paramagnetism occurs in case of free electrons in metals. Previous case, I was talking about localized dipole moments. Now I am talking about free electrons. And if you remember, free electrons actually behave like very, very tiny magnets. So it is as if there are too many tiny magnets which are floating there inside your system. Okay, the result, but they are not fixed as Langevin assumed, but they are free. They are free to move here and there. They can move anywhere. Okay, and because of that, the Langevin theory may not apply to such a system. And that is indeed the case. That, as I told you, that there is no 1 over T dependence. What Langevin expected was that when you increase your temperature, all the electrons, all right, they will start to randomize here and there, all right, and therefore the susceptibility will go down like this. But as I told you, that in this case, the susceptibility actually remains almost constant with temperature. So why that is the case? Why this particular expression, which we expected to hold true, does not hold true? Okay, how is it possible? Why it is happening that it appears as if there is no randomization effect that is occurring as we increase the temperature? So for that, we have to go into quantum statistics and we have to use what are called as the Fermi-Dirac distribution. I will not go into the details of Fermi-Dirac distribution, what it is, but it holds for materials which have half integral spin, as is the case with electrons, and those materials or those particles are called as fermions. So what happens here is that you have your band, okay, and that band is filled from some energy level up to some maximum energy level, which we'll call as the Fermi energy. So all the states below it are filled and all the states above it are empty. Okay, this is when you have not applied any magnetic field. That means I'm talking about the zero field. Here you have both kind of electrons are there. You have down electrons also, and you have spin up electrons also. Now what happens when you apply a magnetic field? Here there was no magnetic field, but now you have applied a magnetic field. So when you apply the magnetic field, then you remember this expression. Okay, so according to this expression, if M and B, they are parallel to each other, what I will do is I will put this M simply equal to mu B. That means I'm assuming that electrons are behaving like tiny magnets whose dipole moment is equal to 1 Bohr magneton. So if you do that, what do you realize is that if your magnetic field and the value of M, if they are parallel to each other, you will find the value will be minus of MB. But if they are anti-parallel to each other, if they are anti-parallel, then you will find that this value will be equal to MB. So if I ask you, what is the energy difference between these two states? Then that energy difference is equal to twice of MB, which can also, as I said, that you can write it as mu B, B also. because electrons behave like tiny magnets having a dipole moment of one Bohr magneton. Okay, so you see that is exactly what is drawn on the right hand side here. Okay, so some of the electrons they lose their energy, which is corresponding to this particular case, and some of the electrons energy is actually increased, which corresponds to this particular state. And what is the energy difference between these two? The energy difference is twice of mu b b. All right, so this total energy difference is twice of mu b b. Now what happens is, think about it. If you want to, what you want to do? You want to change the direction of this. Okay, so if they are pointing in the upward direction, their magnetization will be pointing in the downward direction, because they are opposite in sign. And here magnetization will be pointing in the upward direction. So what the electric field is trying to do is, it is trying to rotate all these dipoles along its direction. That is what this magnetic field is trying to do. But can they rotate? So if they have to rotate, basically what has to happen is that the electron will have to move from this part of the band to this part of the band. That means they have to make a transition from here to here. Then only they can rotate, because on this side only spin up electrons can be there, and on this side only spin down electrons can be there. So they have to make a transition from this side to this side. But as you will notice, electrons which are over here, they cannot make a transition because there are no empty states here. Empty states are required because of Pauli's exclusion principle. It says that if the state is empty, no other particle can come there. All right, but there are some small number of electrons which can actually make a transition, and those small number of electrons are over here. So you see that these states are empty. So what can happen is that these empty states can be filled by these filled states, and you will have a situation something like this. So what that situation will look like is this, that you will have levels filled up till this particular point. Okay, and all these levels will be empty. Okay, so you have a situation something like this. Okay, so you see that there were a lot of electrons, but only a fraction of those electrons were able to make the jump, not all of them. And what was that fraction of electron equal to? That fraction of electron was equal to T over Tf. What is Tf? Tf is called as the Fermi temperature. What I can do is I can put this Fermi energy equal to Kb times of Tf. Okay, so this is called as the Fermi temperature. Okay, and this value of T over Tf, this value is actually very small. It has a very small value of 1%. But we don't have to worry about this value right now. The thing to notice here is that this was the Langevin part which we were expecting. Okay, and this part, the second part, this part is coming from the Fermi Dirac statistics. Okay, and here if I combine these two, then you realize that this temperature factor will get cancelled. Okay, and now you see that the quantity that you are getting is some constant quantity. It is independent of temperature. Okay, so this is what Pauli paramagnetism was. Okay, and remember that this Pauli paramagnetism is not due to localized moments, it is due to the conduction electrons. Okay, and this paramagnetism is independent of temperature. It does not depend upon temperature. So I have a few more minutes. So in those few minutes, I will discuss one very interesting application of paramagnetic materials. Paramagnetic materials are not the materials. They are basically, in real life, they will look like non-magnetic materials. It will appear as if there is no magnetization in these materials because it is a very feeble effect. So they are not magnetic materials in that sense, but they have a very important application, which is if you want to achieve temperatures much below or very close to 0 Kelvin. If you want to go to some sub millikelvin temperatures, then these paramagnetic materials are used. So let us discuss that. So that what we are using is called as the adiabatic demagnetization. What is adiabatic demagnetization is that, let us say that you have some space and you have filled this space with the paramagnetic material. What you want to do is you want to achieve very, very low temperatures. Let us say 1 over 1000 Kelvin. You want to achieve temperatures as low as this. By the way, this temperature is lower than the temperature you will find in space, in outer space. This temperature is lower than that temperature also. And sometimes such kind of temperatures are required for quantum qubits to work. And that is why you will see that quantum qubits are not, or at least why they are so expensive and why they are so difficult to make, because of many, many conditions. And one of that condition is that you have to go to some very, very low temperatures. So I'm showing you that how paramagnetic materials can be used to do that. So let us assume that you have filled this particular space with paramagnetic materials, okay? And you are cooling it in presence of a strong magnetic field. You have applied a magnetic field and then you are cooling it. So what you can do is you can go to very, very low temperatures such as 4.2 Kelvin using helium also. Liquid helium is easily available. Okay, so using the liquid helium, you can dip everything into the liquid helium and you can arrive at temperatures of the order of 4 Kelvin. So that is what you have done. So why we are doing all this, why we are applying a strong magnetic field and then why we are cooling it so much is because what we want to do is we want the Langevin function to approach the value of 1. Okay, and this value of 1 will be approached when x is very, very large. Okay, and if you remember what was x, the value of x was equal to mb over kt. So you are increasing the value of b too much and you are decreasing the value of temperature too much, so that this value of x is very large and therefore x is approximately equal to 1. What that would imply is that inside this paramagnetic material, all the spins will be pointing in the same direction. Okay, so once you arrive at this particular situation, what you do is you thermally isolate your system. Thermally isolate means that you are disconnecting it to the outer world so that no external heat can come inside the system. So you are thermally isolating the system and then now you are slowly turning off this magnetic field. You are decreasing this value of magnetic field very, very slowly. So what will happen when you decrease the value of B? The value of X will start to decrease. Value of X will decrease means what? This order will try to randomize. Everything will try to become random. And to randomize things, it requires some heat. Okay, because some heat is required to always randomize the system. So from where that heat will come? That heat will come from the environment, or that heat will come from the sample that you have placed inside it. So what happens is that you reached at around 4 Kelvin, and after that, because of this randomization effect, the thermal heat is extracted from your paramagnetic material in randomizing the dipoles. And because of that extraction of heat, the temperature actually decreases to few thousandths of a degree. That is what I was telling you before. So this was a very, very simple and very fascinating application of paramagnetic materials, where you can use paramagnetic materials to arrive at temperatures which are just very, very almost close to 0 Kelvin. Obviously, you can never go to 0 Kelvin, but they are very, very close to 0 Kelvin. All right. So that is it from my side for this particular lecture. If you have any questions, I'll be happy to take them.
Participants, if you have any query, please write in the chat box. Sir, there is one question. Which
Hmm.
kind of magnetic material plays a crucial role in quantum technology?
Okay, so all kinds of magnetic materials play a crucial role in quantum technologies. In the last class, we talked about the diamagnetic material, and I told you that superconductors are one of the best examples of diamagnetic materials, and several of the qubits and many of other things, for example, levitation vehicles, they are all built on the superconductivity principle and the diamagnetism principle. So that was about the diamagnetic material that we discussed yesterday. Today's class, I told you that paramagnetic material we have discussed, and I told you that how you can achieve temperatures very, very close to 0 Kelvin, which are required to realize many of the nanomaterials or the materials which are working for the quantum technologies. So in that sense, you have that application of paramagnetic materials. In case of ferromagnetic materials, I will discuss in the next section, in the next class, when I will talk about the ferromagnetic materials. So ferromagnetic materials are actually the materials which we call them as magnetic. Okay, so whenever we talk about magnetic materials, we are generally talking about either ferrimagnetic materials or ferromagnetic materials. So I'll discuss those materials and their applications in the next class. But whatever we have discussed since yesterday and today, so those applications I've told you just now.
Sir, the other question is, can you please explain the role of F orbit electrons in RE materials and its role in quantum technologies?
So when I talk about ferromagnetic material, then all those ferromagnetic materials are either the rare earth ions or the transition metal ions. So either they will be rare earth or transition metal. So the magnets that you see, for example, fridge magnets, they are all based upon rare earth ions. And therefore, you will see that in EV, and if you are following economy also for some time, then you will find that this China's role is very, very important in developing the EV technology. Why? Because it is a major supplier of rare earth ions. So rare earth ions are not only used in or going to be used in the quantum technologies, but they are being used in current technology also. So that is why that is the role of rare earth or transition metal. Both of them are what are actually called as magnetic materials. And why that is the case? Because I told you before also that in case of rare earth, the magnetism is coming from the F electrons, and in case of the transition metals, the magnetism is coming from the D electrons. And why F and D? Because both of them have localized dipole moments. That is the reason.
Sir, there is one more comment. Ranjan Tang is saying it was a very nice lecture, and he wants to ask, can you please share your comment on alternate magnetism?
Okay, so altermagnetism is a different kind of magnetism that is being studied nowadays. So it is, for example, one use of ferromagnetic material is something like this. For example, you have a ferromagnetic material and you have a current over here. So what these ferromagnetic material do is in the current, you have both kind of spins, up and down spins, but when they emerge on the other side, you have only one kind of a spin. Okay, so they are used, these ferromagnetic materials are used for spin polarized, for creating spin polarized currents. Spin polarized currents. So these are ferromagnetic materials in which the spins are along the same direction. But in antiferromagnetic materials, the spins are in the opposite direction. Something like this. What happens, especially in case of altermagnetic material, is that they look like uh, antiferromagnetic material, but they have this wonderful property that they can produce spin polarized currents. So in altermagnetic materials, what happens is that, let us say, they are anisotropic materials. Anisotropic means that they have different properties along different directions. So what can happen is that along one of the directions, they can supply you spin up electrons, and along the other direction, they can supply you spin down electrons. Okay, so they look like uh, antiferromagnetic materials, but because of their direction dependent magnetic properties, so therefore they have been given a different name, which is called as the altermagnetic materials. So these altermagnetic materials are very, very important to realize spintronics devices and some of the other quantum technology devices as well. So people are studying these altermagnetic materials where they are restudying the systems that they previously thought were antiferromagnetic. Now they are studying altermagnetic materials. But to go into further details, you have to actually look at their actual band structure. I don't have the band structure right now with me, but if you look into the research papers, you can find different band structure. For different K values, you will have spin up electrons. For different K values, you will have spin down electrons. And that is what leads to this anisotropy I was talking about.
Okay, thank you so much, sir. Uh,
Uh, Jyoti, can I take 1 minute?
yes, sir, sure.
My voice is audible.
Yes, sir.
Okay. So thank you, Dr. Abhinav, for your second lecture in this FDP. And I have seen that you have already answered all the questions, though I was a bit late in joining here. So now I think we can take a break of 5 minutes, and then again we can join around 3 minutes after 4.
Okay. Yeah.
So
Thank you so much.
yes, thank you. So all the participants, we will take a break of 5 minutes, and then again we will join at 4:03 or maybe 4:04. So okay, now I can just mute my microphone. Thank you. Uh, Ankita, can you hear me?
Yes, sir.
Okay. So, participants, I again welcome you all for this second lecture by Dr. Abhinav Pratap Singh, and that lecture is about the ferromagnetism. He has covered many topics already about the magnetism and their correlation with the quantum technologies. So now in this lecture, he would be covering about the ferromagnetism and other related topics. So may I request Dr. Abhinav Pratap Singh to please start your lecture?
Yeah, sure. Okay, thank you, Dr. Rahul. Okay, so this will be my last lecture uh, for all of you, and this is also probably one of the most important topics, uh, at least from the applications of point of view, because as I said before also, whenever we are talking about magnetic materials, we are basically talking about ferromagnetic materials mostly. Yes, there are some very important applications of antiferromagnetic material also, but for a normal person, ferromagnetism is basically magnetism. So let us see what is ferromagnetic behavior. Uh, so if we look at this paramagnetic, again, if you look at these two curves, these are M versus H curve. M versus H curve means that you have some kind of a material, okay, and you have applied some external magnetic field H to it, and you are checking that what is the magnetization that has developed inside that material. So for diamagnetic material, it is slightly negative. For paramagnetic material, it is slightly positive. You can see that the paramagnetism is fairly large as compared to the diamagnetism. Therefore, even though diamagnetism is present in all the materials, doesn't matter which material you're talking about, diamagnetism is always present. Okay, but if none of the other things are present, for example, neither paramagnetism, nor antiferromagnetism, nor ferromagnetism, ferrimagnetism are present, only then you can observe the diamagnetism. If paramagnetism is there, then diamagnetism will also be there, but you will not be able to observe it. Why? Because the paramagnetic behavior or any kind of magnetic behavior is much greater than the diamagnetic behavior. So this is what happens in case of diamagnetic material. It slightly decreases when you apply a magnetic field. And in case of paramagnetic material, it is along the direction of H, therefore this value is positive and it increases linearly with the magnetic field. But there are certain kind of materials for which if you notice the values on the x-axis here and the values on the y-axis here, then the result will be quite surprising. You will find that for these values, such a high value, also the changes were not so strong. But here you can see that even for smaller values, such as 100 Oersted, the values of the magnetization that are developed are quite large. You can see that this value is 2000 over here, and this value is only 0.5 over here. So these materials are what are ferrimagnetic material or ferromagnetic material, or in our general language, as we say, magnetic materials. So what I want to discuss in the remaining part of the lecture is that how is it possible that such small magnetic field can produce such a large magnetization? That is the whole point of the rest of the lecture. So this picture again is coming up, which I discussed in the last lecture also, that for paramagnetic materials, all the dipoles are randomly oriented. There is no interaction here. For ferromagnetic material, ideally, what we expect is that all the dipoles are pointing in the same direction. Okay, and to achieve this state, you require very small applied magnetic field. Very small values of magnetic field are required. Okay, and you can see that they are aligned in the same direction, all these dipoles. This is actually not true, because if you have read about domains, etc., then you must be knowing that there are different domains. Within the domain, this picture is true. But if you look at the whole solid, then the whole solid may be divided into different domains. One domain may be pointing in this direction, the other domain magnetization may be pointing in the other, and so on and so forth, such that the net magnetization can still be zero. But for ferromagnetic materials, once you magnetize it, then it generally retains some magnetization. So that is what is shown over here also. So what you do is that you started with zero magnetization, you increase the magnetic field, it's saturated. That means previously the magnetization was increasing, it's saturated. Now if you increase B, nothing happens. But if you decrease the value of B, it does not go to zero. It gives you some finite value even if you have completely removed the magnetic field. That is exactly what happens in case of magnets. If you magnetize a magnet, it always stays, unless and until you demagnetize it, it always retains some magnetization. And therefore, this is called as retentivity. Whatever residual magnetization is left, that is called as retentivity. So my lecture is not so much based upon what is retentivity, what is coercivity, which kind of material will have larger retentivity. If you have a lower retentivity, then what will happen? If you have a larger retentivity, then what will happen? Then which kind of material will be more suitable? I'm not discussing all these things in today's lecture. What I'm discussing is I'm talking about the physics behind this magnetism, and specifically ferromagnetism. So in these ferromagnetic materials, this middle one is the ferromagnetic material. Okay, and you can see that for this ferromagnetic material, this value of chi, if you go beyond a certain point, which we'll call as Tc. T stands for temperature, C stands for critical temperature I'm talking about. So if you go beyond a critical temperature, then the behavior is like a paramagnet. That means what has happened beyond Tc is that this thing, ferromagnetic material, becomes as if it is a paramagnetic material for T greater than Tc. So whatever coupling was there, this spin was forcing this spin to align in the same direction, this spin was forcing this spin to align in the same direction, and so on and so forth. But what has happened is that this communication channel that was there, that was broken by thermal energy, the same culprit. So what happens is that if you increase the temperature, this thermal energy increases, it randomizes everything, and therefore the material behaves like a paramagnet. So that is what you can see in this diagram also, that beyond Tc, they behave like paramagnet. This is true for antiferromagnetic material also, but we are not discussing antiferromagnetic material today. So if someone is discussing antiferromagnetic material, they will be talking about again the same thing. And the same thing happens in case of antiferromagnetic material also, that here also it varies as it is not exactly 1 over T, it is actually 1 over T plus some angle, some value theta. Okay, but the main idea is that beyond this Tn, these antiferromagnetic material also behave like paramagnetic material. And the same logic applies here also, that when you have applied a temperature greater than the Niels temperature, someone asked this question in the previous session, that what is Niels temperature, and I said that whenever this interaction between the magnetic ions, when that is broken at that temperature, that is called as the Niels temperature. And once that interaction is broken, everything gets randomized. So again, you get a paramagnetic behavior. So this you will find for all the magnetic materials, that at a high enough temperature, they start behaving like paramagnetic materials. So the topic of today's lecture is molecular field theory, or Weiss field theory. So Weiss, when he gave this theory of ferromagnetism, there was no quantum mechanics at that time, and the electron itself was discovered just 10 years before. So what was the hypothesis of this Weiss? He said you have these dipoles inside the ferromagnetic material. Maybe they are pointing in some other direction, maybe. All right. Now, inside this ferromagnetic material, there is a field which is called as the molecular or exchange field. Okay. And this field is given by this expression. So if this has some magnetization, let us say magnetization M, then there is an internal field and that internal field is proportional to this magnetization. And then there is obviously a proportionality constant. So this was the main assumption of Weiss molecular field theory. Okay, and now we can use our well-known Langevin theory to arrive at some well-known results of ferromagnetism. And let us see, that is what we are going to do next. We will see that if we take this very simple assumption, that there is a molecular field here inside the inside your ferromagnetic material, okay, and that is proportional to the magnetization of the material. We don't know right now, we don't know what is the origin of this field. I'll talk about the origin of this field later on, but for the timing we'll assume that there is such a field. So if there is such a field, and if we are talking about the paramagnetic phase means that when the temperature is greater than the critical temperature, what happens in that case? So in that case, the total magnetic field will be given by whatever field you have applied plus whatever the internal field is there. Okay, now what you can do is you can put this internal field equal to lambda times the magnetization. Okay, and if you apply the Curie-Weiss law, what the Curie-Weiss law says is that chi m varies as some constant over temperature. And how you can write chi m? Chi m can be written as mu naught m over b. So this becomes c over t, where this b is now the total magnetic field. So if I do that, then what will I get? I'll get mu naught m over b total. And what is b total equal to? That is equal to b plus lambda times m. That will be equal to c over t. So what you can do from all of this is you can calculate this value of m. All right, you can separate the variables, and it is an easy thing to do. And you can separate the variables and find out this value of m. Okay, so this value of m turns out to be this quantity, where b is magnetic field, c is this constant c. All right, mu naught obviously you know, t also you know, lambda is again this parameter. Okay, and c is again that constant. So you get this value of m, and now you can find out the value of the magnetic susceptibility. So what is magnetic susceptibility equal to? Mu naught m over the applied field. So if you do that, what you find is that the susceptibility is given as c upon t minus theta, where theta is equal to lambda c over mu naught. All right, and if you remember in the graph that I showed you previously, in this particular graph, again you had a similar expression. All right, you had that same value. Okay, in that case I have written theta over here, but here it is written as tc. That's okay. So you see that it is this molecular Weiss field theory. This is explaining the experimental result that once you go beyond tc, then how should the magnetic susceptibility change? Okay, so that is what is being explained by this molecular Weiss field theory. Now in this expression that we have derived, you can notice, all right, and mathematicians and even the physicists always notice all these things, that denominator can become zero when t equal to theta, and when that happens this will diverge. Okay, so therefore what happens at t equal to theta is that there is a divergence in this. All right, and therefore you will notice that in this case it was written as complex behavior. Obviously the susceptibility will not go to infinity, all right, but it shows some complex behavior. And whatever we have derived here, this does not hold, because remember, this holds only in the paramagnetic case when t is greater than tc. And this kind of a molecular field can be taken for ferromagnetic material also. It can be taken for antiferromagnetic material also. So when theta is greater than 0, we will say that our material is ferromagnetic, and when theta is less than 0, we will say that our material is antiferromagnetic. So in our case, you can see that this value of theta turned out to be positive. That means we were talking about ferromagnetic materials. So here what we can do is we can get an estimate of this value of BE. BE, if you remember, was this molecular field where we assume that we have our material and which has some magnetization. Let us say we have some magnetization, okay, and then there is an internal field, all right, which we called as BE, the exchange field, which was again proportional to this value of M. So what is the order of magnitude of this value of BE? And remember, if you have a very strong magnet, then for a very strong magnets, at least the magnets that you may see in your real life, for example, for Hall measurement, the magnet that we use is generally of the order of 0.5 Tesla. Okay, so generally 1 Tesla is considered to be quite a large magnetic field. Okay, now let us see what is this, what is the order of magnitude of this BE. So how do you calculate that order of magnitude is, now this magnetic field is trying to align the dipoles, okay, and that energy will be of the order of Bohr magneton times this magnetic field. And at Tc, what Tc does, if you remember, Tc is a temperature so large that the thermal energy is of the order of magnitude of this energy. That means it should be equal to kb Tc. So from here we can get an estimate of Tc, which will be equal to mu bb over kb. Now if you remember, okay, sorry, I wanted an estimate of B, not an estimate of Tc, because Tc generally we know, so we wanted to get an estimate of Be. So Be will be equal to kb Tc over mu b. Now this is the Boltzmann constant, which is of the order of 10 to the power minus 23. Tc is generally of the order of thousands, and this mu b is of the order of 10 to the power minus 24. More accurate values are given over here. So you will find that this is of the order of 1000 Tesla. Okay, and remember what I told you was that even 1 Tesla is a very large magnetic field, and probably you might not have seen such magnetic field. So if you see some hoardings of uh, scanning centers, for example, where MRI is there, magnetic resonance imaging. So in that magnetic resonance imaging, they have a magnet there. Okay, and you will find that somewhere you will find 40 is written, somewhere you will find 70 is written, and so on. So what is 40? What is 70? This is the maximum magnetic field that they have. Larger the magnetic field, better is the contrast. So 7 Tesla is much better as compared to 4 Tesla. And you can see that these are very high-end equipments. So even in those high-end equipments, you have magnetic fields not crossing 10 Tesla, for example. And here we are talking about 1000 Tesla, which is like 100 times greater than the magnetic field that you might find in most sophisticated equipments. So therefore, this internal field, this is a very strong magnetic field. Okay, so just keep that in mind. And therefore, because of this very strong magnetic field, again, let us go back to this thing. So what happens is that internally itself, the magnetic field was very strong. This was very strong, right? Be. And now what you have done is you have applied, let us say, an external magnetic field also now, H or B, whatever you want to call it. So therefore what happens is now the magnetization very fastly it saturates. That means all the dipoles align very fastly along the direction of the external magnetic field. So that is why you see that this saturation appears very fast at very small magnetic fields. For example, you can see that this is 100 and here we were talking about 25,000. So at very small magnetic fields this happened. Remember, this is in Oersted, this is not in Tesla. And the magnetization is also quite large as compared to the paramagnetic or diamagnetic case. Because here almost all the dipoles align very fast along the direction of the external magnetic field. So that is why this saturation happens so fast and the value is so large. The magnetization value is so large. All right. So You can get this value of spontaneous magnetization also here. What is spontaneous magnetization? Spontaneous magnetization is that you have a sample, okay, and you have not applied any magnetic field. So this external magnetic field is zero. So even if you have not applied any magnetic field, still this material can have some magnetization, and that is exactly what happens in case of a compass needle. What is compass needle? It is a needle of ferromagnetic material. Okay, and why it points along the north-south direction? Because it retains some magnetization. It has some finite magnetization, even though we have not applied any magnetic field. So that is why it aligns along the north-south direction in presence of the Earth's magnetic field. All right. So this is called as spontaneous magnetization. That even though we are not forcing it, it is by itself having some magnetization. So what you can do is you can get an estimate of spontaneous magnetization, and you can see that how it should change with temperature also. Okay, so let us see how we can do that using the molecular Weiss theory. All right, so again, as I said, that because we are talking about spontaneous magnetization, therefore we are assuming that the external magnetic field is zero. So if the external magnetic field is zero, the total field is simply equal to the internal Weiss field. That means V total will be equal to simply BE. Now, there are two ways to calculate the magnetization. One way is to use the Langevin theory. According to the Langevin theory, this should be the magnetization. Remember, this was the Langevin function. Okay, but if you remember, what was BE equal to? BE was equal to lambda times magnetization. So from here also you can find out the value of magnetization, and you get the value of magnetization as BE over lambda, which is written over here. So you see that now you are getting two different values of magnetization. One is according to Langevin, and the other one is because of the Weiss approximation or assumption. So which one is correct? Both are correct. But if both give you different values, then what is the correct value? So the answer is very simple. So what you do is you plot the Langevin function or the expectation according to Langevin. Okay, and you also plot the straight line that you can see. You plot that also, which is the Weiss approximation or assumption. Okay, and can you guess what would be the spontaneous magnetization? Wherever these two lines intersect. So whenever these two lines intersect, you get your spontaneous magnetization. Okay, so you see that you get a value of spontaneous magnetization by this very, very simple theory, which has just one parameter, which is lambda. That's all. Okay, and even lambda can be determined using some equations, which we'll see. By the way, in these things, lambda, gamma is used. Gamma is basically the same as lambda, so don't worry about that. All right, so this should have been lambda. So there is a slight error in all of this. I should have put lambda here because I used lambda previously. All right, so that is how you can find out this value of spontaneous magnetization. And what is the effect of temperature on spontaneous magnetization? So naturally what we expect is that if you have a material which has some spontaneous magnetization, and if you increase the temperature, what you expect is that there will be some randomizing effect. If you increase T, that will randomize. Okay, so our natural expectation is that the magnetization should go down. But let us see how we can do that. So to do that, remember what was the value of X, right? So the value of X was equal to M times magnetic field, which in this case is BE over KT. Okay, now in this case I can substitute this value of BE as lambda times magnetization. That is exactly what I've done over here. So from here you get this value of magnetization. So this value of magnetization is KBT over M lambda times X. By the way, here even though alpha is used, this should have been X. Okay, so X is same as alpha. So you see, if I plot between magnetization and x, it should be a straight line, and this should be the slope. Okay, so this is the slope tan theta. This should have been equal to this whole quantity kBt over m lambda. Right? So what happens if you increase the temperature? Basically, the slope is increasing. Right? So if the slope is increasing, then what happens? So if I increase the slope, basically what happens is that it will go like this. Okay, and now you see the spontaneous magnetization, which is given on the y-axis. Okay, so my drawing is not so good actually, but basically what happens is that as you increase the temperature, this slope increases, all right, and the value of spontaneous magnetization basically decreases. Okay, so this was the value of magnetization at some temperature, let us say T1, and now this is the value of spontaneous magnetization at some temperature T2, where T2 is greater than T1. All right, so clearly you can see that this m of T2 is less than m of T1. That means the magnetization is decreasing with temperature. So you get this estimate, the correct estimate for how the magnetization should change with temperature using the Weiss theory. Now, you can see, you can keep asking this question. What happens if I keep on increasing the temperature? Now what will happen is that a situation will arise that your line, this sloping line, is now actually tangent to this particular curve at x equals to 0. And this is the condition where if you increase the temperature further, you will enter into the region of paramagnetic materials. So therefore, this temperature should correspond to the critical temperature. And you can use this fact to get the value of critical temperature. So how do you do that? Remember, this value of magnetization according to this formula will be given by this formula, where now you can see that T has been replaced by Tc. Right? So this is the value of magnetization according to this formula. And according to the Langevin formula, the value of magnetization will be given like this. And at x equals to 0, if you remember, this value of Lx is approximately given by x upon 3. So I can do that. Now I can cancel x on both sides, and I get an expression for the critical temperature. And you can see now you are getting an expression for critical temperature in terms of this parameter lambda and in terms of the magnetization of the individual dipoles. So you can work the other way around also. For example, for most material, we actually know the value of Tc because we can measure. All right, and this value also generally we know. So what you can do is you can calculate the value of lambda also, if you like. So you can work both ways. So you see that what this Weiss theory is doing is that it is correctly explaining the temperature behavior in the paramagnetic region. It is correctly predicting how to calculate the spontaneous magnetization and how the spontaneous magnetization itself will change with temperature. And finally, how to get this value of the critical temperature. So what is the origin of this Weiss field? We have been talking about this Weiss field, but I have not told you from where it is coming. So for that, we have to understand what is called as the Heisenberg model. So what is this Heisenberg model is that let us say that you have two spins here. They are pointing in some direction, all right? This spin is Si, let us say, and this spin is Sj. Then their internal energy depends upon the relative orientation of the spins, as you can see from this formula. Okay, it is saying that this internal energy is depending upon some constant, which we are calling as J, then the dot product of Si and Sj. All right. Now this value, this J, this is actually called as the exchange integral. and its value depends upon the overlap of the charge distribution. For example, if you have these two charges, all right, these two spins are there, and their charge distribution is something like this. Something like this. So you see that there is an overlap of charge distribution. So this value of J actually depends upon this overlap. So it can be some complex function of this overlap, and therefore it can also depend upon the relative distance between these two spins also. But we will not go into that details. What we will simply assume is, by the way, this value of J can be positive, it can be negative also, but for the time being, let us assume that this value of J is positive. Now let us see what this is telling you. This is telling you now is that if you take value of U, then it will be equal to minus 2J S, let us Si Sj, all right, when Si Sj are parallel to each other. Si Sj, when they are parallel to each other, then this is the value you will get. And when they are anti-parallel, then you will find, because the angle between them is now 180-degree, so dot product will contain a cos theta term that will become -1, and now the energy will be plus of 2J Si Sj. That means this will have a lower energy, this will have a higher energy. So this will have parallel configuration, and this will have a anti-parallel configuration. All right. So system will actually prefer this state, and this is the case for ferromagnetic material. So therefore, we say that for the ferromagnetic material, the exchange integral is positive. And that situation flips if J is less than 0. Okay, that means let us say that mod of J is equal to let us say that J is equal to minus of some mod of J. Then, as I said, the situation will flip. Now, if you have parallel alignment, then the energy will be equal to 2 mod of J S1 or Si Sj. And if you have anti-parallel alignment, then the value of U will be less. That means the system will prefer this state. Okay, and this is the case for antiferromagnetic material. So you can see that whether the magnetic material will be ferromagnetic or antiferromagnetic, that can be judged from the sign of this exchange integral. Larger the magnitude, stronger will be the underlying order. For example, if it has a large negative value, the ferromagnetism will be strong, its transition temperature will be, or critical temperature will be, high. If the value of J is negative but small value, then the value of Tc will be small. That means it will not be a very strong magnet. And this is the reason for, this is the origin for the molecular Weiss field. This interaction leads to the Be that we were talking about previously. So you see that Be is no magnetic field at all. It is actually an electrostatic field, but it behaves as if it is a magnetic field. All right. So remember that there is no magnetic origin to this magnetic field, even though we are calling this as a magnetic field. So instead, it is better to call it as a exchange field or molecular field. So this exchange field or molecular field has electrostatic origin. It has nothing to do with magnetism, but it causes magnetism. Okay. In itself, it is not a magnetic field, but it causes magnetism. So that is how this comes about. And I will give you one qualitative explanation again, that why it can happen that in some cases parallel alignment may be favored. So let us look at that explanation also. So let us say that you have two atoms, all right. In one of the atoms, you have spin on this direction, and in the other atom, you have electron in this direction. Now, both these electrons have negative charges. So they don't like to be close to each other. What they prefer is, they prefer to be as far apart as possible. Now, think about it. If this electron wants to come over here, okay, will it be possible for this? Let us call this as electron number 1 and this as electron number 2. So, will it be possible for electron number 2 to arrive at the site of electron number 1? No. Why not? Repulsion will be there, that is correct. But the other problem is Pauli's exclusion principle. Pauli's exclusion principle. That will not allow this electron to go to the site of electron number 1. Why? Because both of them have parallel spins, and if they want to come to the same site, their spin should be opposite. So therefore, this transfer is not allowed, and therefore they are far apart, and therefore they will have low energy. Let us look at the second situation where the spin is actually anti-parallel to each other. Again, let us call this as site number 1, site number 2. Now, is this possible? Yes, it is possible. Okay, but if they do get transferred, what it will do is that it will increase the energy of the system, and therefore this becomes a high energy system. Okay, so out of those two, which one will be preferred? Case number 1, let me call this as FM case or AFM case. FM or AFM. FM means ferromagnetic, AFM means antiferromagnetic. So what can happen is that this ferromagnetic case can be more energy wise, it will be more favorable. So that is the reason why in some cases you can have this value of J to be positive. That is exactly what happens over here. It actually lowers the energy, the electrostatic energy of the system, and everything depends upon this Pauli's exclusion principle. So that is the origin of the Weiss molecular field. So that is all I wanted to discuss about the Weiss molecular field and about the ferromagnetism also. I did not want to go into the explanation of the hysteresis curve because that will require a lot of discussion about domain walls, domains, impurities, role of impurities, magnetocrystalline energy, and things like that. Exchange energy, the competition between the exchange energy and the magnetocrystalline energy. So all these domain walls, the width of the domain walls. So that is why I thought that I will not be able to cover that part in this particular lecture. But obviously those things are very, very important. So I wanted to discuss the physics behind this paramagnetism. That is exactly what I have done. And lastly, I just wanted to tell you that the means one lecture or even 10 lectures are not sufficient to tell you that how important these magnetic materials are. And I have listed just some of them over here. And in these applications that I have listed here, these are, as I said, these are just some, a very small subset of applications where you use magnetic materials, not just in the existing technology, but in the future technology as well. So, for example, if you want to produce magnetic field, then you use an iron core. I don't know whether you thought about this question before or not, and then you wound some wire on this iron core, and then you pass some current into this iron core. Fine, the magnetic field is produced due to this current. But why this iron core was required? Okay, so previously that used to confuse me, but when I read about ferromagnetic material, then I realized that inside the ferromagnetic material, the magnetic field is very, very large. That is what creates magnetic field. All right, so ferromagnetic material is used to produce magnetic field even in the electromagnet also. Okay, and the same kind of a principle is used for transformers also. You know that for transformers, this thing is used, right? So for transformers, what you want to do is you generally want to link the magnetic flux. So what you do is you take one coil on this side, the other coil on this side, and again these coils are again made of ferromagnetic materials. So in the transformers, we use ferromagnetic materials. For inductors and generators, we use magnetic materials. So if you know how the generator works, then you must be knowing that magnetic materials are used there. in the loudspeakers, the headphones that you might be using, the headphone that I'm using presently, that also has these tiny magnets, motors, locks, etc. MRI, I've already told you that in case of magnetic resonance imaging, again, you require a very, very strong magnet. And for other biomedical sensors also, you require magnets. There are many, many sensors for which, again, these magnetic materials are required. Sensors might be sensing magnetic field, their position, speed, etc. Memory uses, I have told you. So previously, even a 5 MB, even a 5 MB memory that used to weigh in tons, hundreds of kilograms. People used to use cranes to transfer these memories from one place to another. They used to use cranes to transfer first in an airplane, then that airplane used to take those memory components to other place. 5 MB, just 5 MB. And right now we are talking about, let us say, 5 TB. Just imagine the difference between these two things. 10 to the power 6 order of magnitude. And this again is caused by the way, this 5 MB was also because of ferromagnetic materials. And this is also again due to the ferromagnetic materials. It is just that we have developed quantum mechanically we understood that how these magnetic materials are working, and then we have reduced their sizes very, very drastically. So this is that is one very, very major application that we use in our daily lives, which is the storage. And then, as I discussed before also, that these magnetic materials now are being proposed to have applications in quantum sensing, quantum information processing, qubits also. And as I said before also, this is just the starting. I can't even list that how many applications these ferromagnetic materials have. So I think that is it from my side. If you have any questions, then maybe we can discuss those questions.
Thank you, sir. Sir, there is one question from Dr. Manoj Kishore. He is asking, generally we treat one magnetic moment present in the field generated by the other magnetic moment. But you explain exchange interaction is electric in origin. Can you explain that in brief?
Okay. So let us say you have two bar magnets. One bar magnet is over here. Okay. And another bar magnet is, let us say, over here. Okay. Then what you will find is because of the magnetic interaction between them, they will be snapped together if they are close enough. That means it will lead to some kind of ordering. Okay. So this is due to magnetic forces. But when we have dipoles, the magnetic dipoles, which we have inside the solid, then what you can do is, I did not do that, but if you have read electrodynamics, what you can do is that if you have some magnetic moment, due to that magnetic moment, you can find out what will be the magnetic field that will be produced at some other different time. And you will find that that magnetic field is very, very, very weak. Okay. And that magnetic field cannot lead to the ordering that we are talking about. And as I said, that the Weiss field, that is of the order of, if I convert them into in terms of Tesla, then it is 1,000 Teslas, which is an extremely, extremely strong magnetic field. Okay. And as I said, we treat this as a magnetic field. It is not an actual magnetic field, but it behaves as if it is a magnetic field, but it has electrostatic origin. So my point is that you have to actually calculate the value, and you have to confirm yourself that whatever magnetic field is produced by one dipole onto the other dipole, this magnetic field is almost zero. It plays no role in the ordering. So that is why I said that it is not the magnetic field which is leading to this ordering. It is actually the electrostatic field.
Participants, if you have any question, please write it in chat box. Uh, Sir, someone is asking which textbook has this explanation. Sir, please inform so that I will read it again.
Okay,
Uh,
so there are many textbooks that you can read. Uh, I will, for example, Kittle is obviously one of the most recommended texts. But if you want to go in the Kittle, generally I find this discussion too. But if you are fan of this book, you can always read Kittle. There is a book by Decker. I find this book to be very, very readable book. Okay, so you can look into the Decker's book. All these books have titles such as Solid State Physics. These are very, very standard texts that I'm talking about. Another very important, excuse me, another very the book which I find very, very helpful in the discussion part is book by Ali Omar. Okay, so these are the books which you can refer to. Okay, and if you are a fan of Ashcroft Merman, then obviously this is always one of the best books to recommend. So these are some of the books. If you ask me if you want me to one book to recommend, then I will say that go ahead and read this Ali Omar's book. This is a very nice text.
okay, thank you, sir. Sir, the next question is, in the perspective of quantum sensing, how can we measure its magnetic dipole variation at quantum level?
At quantum level, you have you have machines which are called as squids. So what are squids are basically Josephson effect. You might be reading later on, and maybe you will read about squids also. So for squids, these are very, very sensitive instruments which can measure very, very small magnetic fields. But will they be able to measure the magnetic field of one dipole? Maybe not. So, frankly, I don't know whether there is such a machine where you can actually sense magnetic fields of one particular dipole. But for example, in case of MRI, when you have some number of dipoles, then those fields can be read very easily using squids. So I may have to check whether squids can measure magnetic field of one dipole or not. That I'm not sure about. But this is one of the most sensitive equipment that you can use to measure the magnetic fields.
Sir, someone is asking regarding the book. Can you provide the titles and the publisher's details here, sir?
Um,
The books you have suggested.
okay, then
Under.
again, I have to go to Amazon and I will have to search that. If you just search Google just by these names, then most probably you will find them. If it is actually required, just drop me an email. I'll request Dr. Rahul to send me a WhatsApp message if it is required. I can reply there also, and then that can be shared with all of the participants.
Okay, sir. Thank you. Sir, there is another question. Can we amplify its change in magnetic field intensity in order to check it?
We can do that. That oscillation is always done. So that is called as the vibrating sample magnetometer. So what is done is that the sample can be oscillated in a pickup coil, and whatever changes in magnetic field that happen, those changes can be very sensitively recorded using the coils. So that due to the Lenz law, that those signals they create a very, very tiny signal, and that tiny signal can be again used to calculate the magnetic moment of that particular material. So this is a very good comment that he has made or she has made.
Okay, thank you, sir. Participants, if you have any questions, please write. Sir, there is one more question. In that case of general information, what's the core difference between the classical magnetic sensor and quantum sensor?
Quantum sensor, okay, let me give you one example. Let me just think about it. So you are asking like what is the difference between a normal sensor and a quantum sensor? So
Yes,
what can
sir.
happen is that, for example, Hall effect is generally used for checking the magnetic field. So what is Hall effect is that you have a material, you are passing some current onto it, all right, and if you apply some magnetic field onto it, then a potential develops across it, okay, and that potential you can measure very very sensitively. So what happens is that this potential is a very sensitive function of this magnetic field, okay. This is called as the Hall voltage Bh. So by measuring this Hall voltage Bh, you can measure this value of the magnetic field. So that is one classical example that I can give you. And quantum mechanically, what you can do is, for example, is that I talked about squids previously. So in case of squids, we use superconductors, and in case of superconductors, if you make a ring of the superconductor, then the flux through this particular superconductor is quantized. So that flux, I don't remember exactly what was the value, but I think it was of the order of h over e, the flux that is quantized inside that particular material. So whenever there are very, very small changes into this magnetic field, then the flux can change in the steps, something like this. All right. So that can be used. That is one way of measuring the magnetic field very, very sensitively. And what happens is that, for example, there are some quantum materials. For those quantum materials, what happens is that we make nanostructures of them, okay, and we measure their transport properties. So when you go at a very, very low temperature, then you find that their resistivity again contains these kinds of steps. And these steps arise due to the quantization of the orbits, okay, and these levels corresponds to what are called as the Landau levels. Okay, so it is not possible for me to give you the complete explanation here, but these are some of the ways where you can actually use some quantum mechanical phenomenon for sensing of, let us say, magnetic fields. So these are just two basic answers that I've given.
Okay, thank you, sir. So the next question is, has any attempt been made to produce an alloy according to the need of quantum or any other purpose?
Alloys have some people work on alloys all the time, and they always try to synthesize new types of alloys which have some novel properties which is generally not found in nature. But as far as magnetism is concerned, magnetism, what you can do is that you can have some, like, whatever block of alloy you have, okay, and there is a limit to how much this block can produce magnetic field. So there are rare earth alloys which are very, very strong. They are so strong that you should not even hold them together in your fingers, because they might snap together and your finger bones might break. So they are very, very strong magnets which exist, very strong alloy magnets which exist. But as I said, that there is a limit to them. It will be very difficult to go beyond 1 Tesla using them. So what is done is that electromagnets are used, and specifically, if you want to go to very, very high magnetic fields, then you have to use superconducting magnets, because the current required to flow so that you get such a large magnetic field is very large, and those kinds of currents can be handled only by superconductors. So electromagnets are used, and specifically superconducting magnets are used, and that is why if you want to go towards 10 Tesla or more than 10 Tesla, then the cost becomes very, very high. Why? Because you have to use superconductors, you have to constantly cool them below their transition temperatures, and therefore it requires a lot of machinery and lot of resources, and cost goes very, very high. But there is a limit, as I said before also, that there is a limit till which alloy can produce the magnetic fields that you require.
Uh, So for electronic properties of material in solid, we treat the electrons as wave and use momentum space to describe the band structure. But to analyze magnetic materials, we talk about spins and SOC, etc. But as a computational physicist, we need to deal it in K space. Can you share your comment on how to think spins at K space?
So this is a very good question. So if you remember, um, okay, so that band diagram I think was in the other PPT. Let me just check. So if you look at this diagram, sorry, let me just get clear it a little bit. So you see, this is a very simplified diagram. Okay. So when you talk about band structure, etc., then what you're basically talking about is that you have K, let us say space on this direction, you have energy on this direction. And if I draw a very simple picture, so it will be something like this. Okay. So there is a dispersion between E versus K curves. Now, if you don't have any magnetic material, if your material is non-magnetic, then all you have to do is you have to calculate everything and simply multiply by 2. Why? Because every state will have an up electron and it will have a down electron. So that is why you multiply by 2. But in case of ferromagnetic materials, you can have states which behave differently for spin up and for spin down. So I did not discuss this in case of ferromagnetic materials, but in case of ferromagnetic materials, for example, you can have a band structure something like this, that even if you have not applied any magnetic field, okay, and let us say that this is energy and this is K, that even if you have not applied any magnetic field, then you might have some magnetic states here and you can have some magnetic states here. That means that some of the states will have higher energy, or if the Fermi energy is like this, if this is the Fermi energy, then you will see. And if I call this, let us say, spin up or spin down, let me call this as spin down, and this one is spin up, then you will find that there are more number of spin down electrons as compared to the spin up electrons. And therefore, there will be a net magnetization in this direction. Okay, which I called as the spontaneous magnetization. So regarding this particle nature of the electron, calculation of the band structure and things like that, all those things are true. And you will find that magnetism actually uses all these concepts. So I have taken a very simplistic derivation part, but if you go to the Kittle's book, you will find that you can do the quantum mechanics of it. You can find out the diamagnetic susceptibility of the electrons by solving the Hamiltonian, and you can do the same for paramagnetic materials also, ferromagnetic materials also. Okay, so all this is actually following from the electron properties of the material, which we are actually plotting in the K space, as he said. So but this is called as the rigid shift model. It is a model, it is not the exact thing, but it is called as the rigid shift model. That means that it is as if there were two bands and they have been just shifted up and down with respect to each other. Okay, so I don't know whether this answers the questions or not, but what I wanted to highlight here was that whatever he said was true. But now what you have to do is that you have to look at which band is corresponding to spin up and which band is corresponding to spin down. And if you remember the discussion on altermagnetic material, so if you go and look at the band structure of that particular material, you will be fascinated to see that why people are find it so exciting, why they are finding it so exciting.
Okay, thank you, sir. It seems like there are no more questions. And before ending this session, on behalf of EICT Academic and MNIT Jaipur, I express my heartfelt gratitude to you, sir. And thank you so much for this wonderful session. And
Okay.
thank you.
Thank you.
Thank
Thank
you.
you so much for inviting me.
Thank you. Thank you, sir.
Thanks to Dr. Rahul and the other team members also for giving me this chance. Thank you so much.
Sir, your voice is not audible.
Uh, am I?
No, sir.
I'm not audible.
Doctor, no, sir. You are audible. Dr. Rahul Singhal, sir. Sir, you are not audible.
All right. So maybe I can leave now.
Yes, sir. Actually,
Okay.
Dr. Rahul Singhal, sir, is microphone is not working. On behalf of him, he is saying I'm saying thank you. Thank you so much, sir.
Thank you. Thank you so
Now,
much again.
yes, participants, you can now leave this webinar. Thank you.